So I want to talk about what is this sort of what we talk about as a vector matrix multiplication. In a very simple term, that says I'm taking an input that is a vector and I'm multiplying it by a matrix that is a stored value. So the inputs are signals, the matrix is fixed because it's a stored value. It certainly could change at a slow scale. And I'm multiplying those things together. Most people would think that's a very typical, in fact, it's what we see all the way through most of computational operations for so many reasons. Okay, so now I really want to, the key is to talk about what is a vector matrix multiplication in analog. And I want to give kind of a high-level perspective on this, but with a very particular focus from both sort of a systems and historical perspective and how we start to see these things. There's a lot to dig into in terms of how do I get multiplication in a single transistor, and we'll go over that briefly. Okay, so if I talk about a vector matrix multiplication, this is something that you see you need, for example, in every neural algorithm, you need in many different cases. And if you're going to do this in an analog form, what you want to be able to do is be able to do this in a reasonable way. And the issue with this traditionally was not so much could I figure out how to could I apply a vector of signals, or could I take a whole bunch of multiplying elements and take all the outputs which are currents, which is exactly what you want to do because you sum all the currents together and that gives you a full output. So that's wonderful. Kirchhoff's current law is great because it's a law and it's a summation. So the summation is perfect. So that's great. I mean, it's nice if it's perfect, it means there's no errors. Yay, we're good. No problem generating an input. It's also not too, but then the question is that how do I not only do a multiplication, which there's many different things you could do there in terms of signals. The question is how would you do the stored values? And if you look at the early sort of elements and discussions in the neural network community, for example, which is where a lot of this started in the early 80s to mid 80s to late 80s to early 90s. The struggle was how do you store these values and still use it in a multiplication? Eventually the conversation was a single floating gate element really is the key element that you want. And then you can talk about other crossbar elements, but it still is by far the sort of shining conversation and shining opportunity here. It is a beautiful 3/4 terminal device, how you look at it. And that floating gate element allows you to store the values. It allows you to do a multiplication. It allows you to be programmed. It allows you to do it in a small area and small power. And all of those are critical. You have to get all those right. Once you get that right, then it turns out that now it's easy to think about how you do multiplication because you could imagine, as in this original structure, that the difference between where these two floating gates are and then effectively their new, say, bias current or threshold, it's not really threshold current, but bias current related to that. They have two different values that makes it look like a current mirror with different ratios. Really done by moving the flat band or threshold voltage, but all that works. And what you realize is you have a current mirror of a certain gain, which is programmable, i.e. a multiplicative gain. You can then do things where, as in this structure, which was designed to make sure I had a perfectly good 4-quadrant multiplier. So I could have a signed input and guarantee I have 4 transistors here, get a signed output for that one. And I could do this in a large array, and I could do a whole linear array of these, and I could do all the measurements around it. Being very, very careful, nice, good linearity, and all the other kinds of properties. This sort of comes from the conversations that happened in CICC 2004, which was to show a vector matrix multiplication very carefully to a good analog circuit community. But it was to show one more thing. It was to then show, by the way, if I change the bias currents of which these are all operating from 25 picoamps to, say, half a microamp, that in fact I could model this carefully in this device, and the actual efficiency, the energy efficiency, which meant that the amount of computations per unit energy was constant, and in fact was constant to a number around 10 to 20 mmax per microwatt. This particular one actually was about 4 to 5. which was a factor of 1,000 over what digital would be. Right now, the digital efficiency wall is about 10 MMAC per milliwatt. At the time of this, the best number was about 4. And you got this factor of 1,000. This was actually something Carver predicted. Carver Mead predicted this originally in 1990. From just simple counting arguments, you would expect to see this. This has been done many, many times. There's a lot of different history around this, including an earlier conversation that kind of, assumed that this would eventually happen, and coined the conversation and the architectural idea of computing in memory. This was in 2001. Because if you think about it, these all look like double EEPROM elements. And so effectively, I'm just running signals into what looks like a double EEPROM array, modified slightly, to give myself a pretty important computation, and this works well. Now I can do this in this form. There's many different architectural forms. This one actually is playing off the gate voltages and current mirrors. Another way to do it would be to actually play off the source voltages and actually look at the summation you have in such a network. Works really, really well. Why would I pick this? Well, this turns out to look a lot like the crossbar fabric in a vector matrix multiplication, or in a crossbar fabric enabling me to do a vector matrix multiplication in a field programmable array, which means that all the routing aspect that you think, oh, that's just to connect things, actually allows you to do a lot more operations than you would imagine. This is quite a huge opportunity because then I can get very efficient computations just in the classical routing fabric that I have to build anyway just to route things. This is pretty amazing. The other aspect that you can see is you can start getting a sense that you can actually model this and model this very carefully. And there's been a lot over the years. Within another 5, 6, 7 years of this work, you started to see multiple aspects of modeling of how this worked across currents, such that it wasn't just a case of I could do analysis, but I could actually turn it around and say, if I need this particular property, I should be able to guess, which if now I'm dealing with programmable FPA devices becomes very, very critical. Okay, and so as a result, you can think about what is bandwidth and computation and power and energy efficiency, which is usually an MMAC per second per microwatt kind of numbers, noise, and SNR. These are all understood parameters. And for the most part, things like bandwidth scale with the current put through that, a certain amount of per additional computation, how much the power is, and it scales in a very, very known way in terms of the parameters are in a very known way. One of the things you'll notice is very critical is sort of the per unit capacitance, because you might imagine the more capacitance, the more effectively KT over C noise or less noise you have. It also changes what your speed is. So it's again all the classical analog design concepts all come into play. If you go above threshold, these certainly do change. As most cases above threshold, it's a diminishing return problem. But otherwise, you get a very, very reasonable thing, and you can design different structures for different sort of capabilities.